Okay, so as I announced on the LMS, so I recorded the video because we missed one class maybe 2 weeks ago, right? So and then I hope everyone watched the video because in this class I cover about not the memory instructions. Okay, so actually because we I already covered the arithmetic instructions and then immediate instructions in the recorded video. Okay, so before starting with today's lecture, I will briefly explain about the lab assignment. Okay, so so I posted the first lab assignment, right? Uh, Here's the lab. Okay. Okay, so actually the purpose of this first lab is making you prepared for the following lab assignment. Okay, so in this lab assignment, you are requested to install the virtual machine platforms such as VMware, or also you can use the actually this is also the virtual machine, so you can use the WSL, the Windows subsystem for Linux, if you are using a Windows operating system. Also, if you are using Mac operating system, then you can install VMware. Okay, so VMware is the virtual machine platform. Okay, so it is because for the following labs, we will use Linux operating systems, and then I believe uh, most students do not use Linux, right? So I believe the most students use Windows operating system or Mac operating system, right? So, but the actually for computer engineering research, so we use Linux operating system, right? Not Windows or not uh, Mac operating system. So, so usually, so you are developing uh, an, an application, then you can use Mac operating system, right? But usually for computer science or computer engineering research, so we use a Linux operating system also, and then so you are learning about the computer system, right? So in this course, we will use a Linux operating system. So which means you may not be familiar with this Linux operating system, right? So I believe everyone is familiar with the Windows or Mac operating system. So it's convenient. And then it means that so these operating systems provide the graphical user interfaces, GUI, but for Linux, so actually we usually use a command line interface for on Linux operating system. Okay, so which means that you can type commands, so Linux commands, then you need to execute some Linux commands or binary files. Okay, so if you are not familiar with the Linux operating system, please start early. So please start this lab early because so actually in the next week I will provide another lab assignment. Okay, so you need to be prepared. Okay, okay. So please start early, and then I believe I provide some detailed instructions for installing the WSL or VMware uh, uh, for Mac operating system. So you can click this link like WSL or virtual. So actually, I also provide the installation instruction for VirtualBox. So VirtualBox is the virtual machine platform for Windows or Mac operating system. But I tested the VirtualBox on Mac operating system, but it does not work well. So I just provide the the installation instruction for VMware. Okay. So, and then fortunately, the VMware is free, right? So it was not free, but actually the policy was changed. So now it's free. So you can use, okay? Uh, okay, so I provide the instructions. And then for the following lab assignment, so we will use a system Verilog for designing the pipeline architecture. Okay, so the final goal of this lab is to design five-stage pipeline architecture. So we will use system Verilog. Okay, so in order to use system Verilog, so we require a simulator or and compiler. Okay, so system Verilog file is just a text file, and it's also the high-level language code. So it needs to be compiled. It's not same to the some compilation process of the normal programming languages, but it needs to be compiled. Okay, and then we need to simulate. So you know so CPUs are digital system, a kind of digital systems. So I mentioned that all digital systems handle digital signals. So we need to check how these signals are processed in a CPU, right? So which means that we need to monitor the changes of digital signals inside of a CPU, right? So which means we need to simulate, we need to check the behavior of the CPU, like the changes of digital signals. So in order to simulate this CPU model, so we also require the CAD2. And then for this course, so we will use Icarus Verilog. Okay. So this is the open source CAD2. And then using the Linux command, so you can easily install Icarus Verilog. So I believe actually for building some environment, so Linux is more convenient. It's more convenient than Windows. Okay, so you can just type the command and then you can just, it's a very, very simple, right? So actually for the first lab assignment, so actually for Mac users, you do not install a virtual machine actually, because so you can install Icarus Verilog and then GTK Wave. So actually GTK Wave is required for monitoring the waveform, okay? Like the changes of digital signals. So actually so you can install Icarus Verilog and GTK Wave using Brew, okay? But for the next lab assignment, you need to install RISC-V compiler. But so for this installation, so actually you may require the Ubuntu environment. So it's a Linux environment, okay, Linux operating system. So even though you are using Mac operating system, please install the virtual machine platform and then also install the Ubuntu, okay, Ubuntu server, okay. So you can follow the instruction, and then also actually I kindly provide the source code and then test bench. So if you are not familiar with this process, then I also posted the HDL material on Piazza. Okay, uh, so do you know? So where is the Piazza? Let me check. So I believe I already provide the required material. Where is the resource? Okay, so it's not easy. Where is the Piazza? Okay. Okay. So if you see the general resources, it's a table, so you can find. So I just select the lecture slides for HDL, right? So like HDL 1, 2, 3, 4, and then I also provide the lecture slides for making test bench. But for this lab assignment, so I will provide the test bench, okay, usually. And then also you can find the several materials. So I collected some information about your some prerequisite. so 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 I okay. so and then I found that about the one over third of students did not take the digital logic design course, right? So so if you did not take the digital logic design course, then please please study by yourself using these materials. Okay. So maybe where is the system where test bench instruction to. So if you this is the YouTube, right? Okay. Also I provide the YouTube link, right? So these are lecture slides. So and then these are YouTube link. So you need to be prepared, okay, before or starting the design labs, okay. Okay. Actually, for the next design, uh, so for the upcoming two design labs, so we will handle actually RISC-V compilers. So you do not know about the HDL, okay? So like the digital design. But since the first lab assignment, 1, 2, 3, 4, right? So you need to know about the syntax, at least the syntax of system Verilog, okay? So please be prepared. So please study by yourself using these materials, okay? So before starting the fourth lab assignment, okay? Any question? Okay, good. Okay, so you can just so if you execute the compiled binary file, then you can get the waveform. So actually, if you execute the compiled binary file, so it's the binary file, not binary file, so it's a somewhat specific file. So this file will be created by equals Verilog, and then using this command bbp, then you can execute the compiled file. Okay, then you can get the VCD file, and then VCD file includes the waveforms of this design, your design, because so BCD is so this file, the TB underbar and the 2.bcd is specified in this line. Okay. So and then you can open this BCD file using GTK wave. Okay, then you can see the waveform of your design. Okay, then you can check how signals are changed inside of your design. Okay, so you can just follow the instructions in this lab document. But if you are not familiar with this Linux operating system, then please start early. Okay, and then uh, if you encounter some troubles, then you can get help from TAs. Okay. Also, you can post questions on Piazza. Okay. 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 So, okay, let's start today's lecture. Okay. Uh, so in the previous class, we learned about the basic instructions. So we learned about the design policy of RISC-V ISA, and then we learned about the operands of instructions. So operands means that it's the data handled by instructions. So this is the ISA design policies, the principles. So okay, and then so this is the simple form of the instruction, RISC-V instructions. Okay, so you can find there are 3 operands, and then for these operands, these RISC-V instructions handle 3 types of operands. So usually the most instructions. So RISC type instructions handle 3 types of operands. So what? Registers, memory, and constant. So immediate. So and then in the recorded video, so I explained about the register type operands and constant type operands. And then this time, so I will explain about the memory type operands. Okay. So you need to remember what are registers. What is a register? What is a register? And so I explained that the register is the small memory space. Okay. So, so I explained that you can just understand that memory is an array that can store data, right? The register is the same. Register is also a kind of memory, so which means that the register is composed of several elements, and actually the number of elements is much smaller than the memory. So which means that the size of a register is very small. And then the size of a register, so which means that the number of registers and then the size of a register, the width of the register is defined by ISA, the instruction set architecture. So that's what we learned. Okay, so so this is the structure of RISC-V registers, the general purpose registers. So RISC-V, so there are 32 registers. So these registers are integer registers. So which means that integer data is stored in these registers. But I mentioned that the X0 is the 0 register. So which means that the value in X0 is always 0. Okay, it's not changed. Also, the RISC-V includes the program counter. A program counter stores the PC value. Okay, that is the address of current instruction is stored in program counter. Okay. So we learned about the immediate type instruction. So immediate represent the very small constant data. Okay. Then this immediate data can be included in the instruction. Okay, so why? Because we can just reduce the number of instructions, right? So that's what I explained in the recorded video, right? And then actually this small constant number is frequently used in our program. So if this number is included in the instruction, then we can reduce firstly, we can reduce the number of instructions. So if we reduce the instruction count, then we can improve the performance, right? So this is the immediate type operands. So now, so we will learn about the memory type operands. So you can understand the registers and memory like this. So this is the CPU, okay? It's a CPU. And then inside of the CPU, there is a register file. So a register file is a group of registers, right? So this is the register file. And then, as I mentioned, there are 32 registers, and then plus PC, the program counter. But what is the problem? So I mentioned that the registers are very fast because smaller is faster in the hardware, right? So registers are very fast, but the size is small. That's the problem. You cannot store large amount of data. Okay, so if you check the file size, you can find that. So usually the file size is very large, so which means that actually data size is very large. Then how can we handle this large amount of data in a CPU? So register is so small. So this is the memory. Okay, so the memory size is very large. Okay, so if you check the main memory size of your computer, then you can find that memory size is around the 8 GB or 16 GB, blah blah blah. Okay, so it's very large. Okay, so compared to the register file, the memory size is very large. But what's the problem? It's large and slow. Register file, small and fast. So when we execute our applications, most data actually exist in memory, right? And then, so in the previous class, we learned about the arithmetic instructions, but actually most instructions handle register data, like add, so add x1, x2, x3. So these are register data, register operands. And then in RISC-V instruction, also all other RISC type instructions, arithmetic instructions cannot use memory type data. Then how can you handle this large amount of data in memory? Obviously, the data needs to be transferred. Okay, in order to use data in memory, firstly, this data in memory needs to be transferred to the register file. Okay, so and then this instruction is called load instruction. So load means that load transfers data in memory to the register file. So firstly, in order to use data in memory, then this data needs to be transferred to the register file, and then using the normal instructions like arithmetic instructions, this data can be processed, right? And then also you can observe that processed data is stored in registers, right? So if you see the add instructions, the destination is also register. Then what does that mean? So data is in here. So if you write the code like a C equal A plus B in C, so these are variables, but when these variables are declared, then actually the memory space is assigned to these variables. So which means in the memory, there is a space for A, there is a space for B, there is a space for C. Okay? So you can understand like this. Variables are declared. Then the memory space is assigned to these variables. Okay? So in a code, so in a high-level language code, we can easily declare some variables, and then we can just assign some data to these variables, and then these variables are handled. But actually in computer hardware, you can understand like this. The memory space is assigned to these variables. Okay? So where is the C? Actually, the C is in the memory. Okay? What does that mean? If we just execute the add instruction, then add instruction stores the data in registers, which means C does not have the result. So what should we do? Register data needs to be transferred to the memory, the memory space assigned for C, right? So there are two types of data transfer between memory and register. The data is transferred from memory to register file, and then this instruction is called load instruction, and then the data in registers can be transferred to the memory. This instruction is called store. Okay? So there are two types of memory instructions. And then the main purpose of memory instruction is to transfer data between registers and main memory. Okay? And then so you can just understand the direction of memory instructions. And then, so memory operands. Memory operands are handled by memory instructions in RISC type ISA. Okay, so which means, so in the CISC type ISA, the memory operands can be handled by some arithmetic instructions, but usually in RISC type ISA, memory operands are handled by only memory instructions like load and store instructions. Okay, so you can just understand this concept. Okay, then I believe you can easily understand about the memory instructions. Okay. Okay. So as I mentioned, register file is too small, so we need to store the large amount of data in memory. So memory, the data transfer instructions are required. Okay. So also the main memory used for composite data like arrays, structures, and dynamic data also are the variables. Okay. And then also I explained about the two types of memory instructions, like load and store instructions, right? Load and store. So you need to remember. So you need to remember the definition of load instructions and store instructions. And then, as I mentioned, memory is byte addressed. So what does that mean? Address 1 is mapped to the 1 byte of data. 1 byte is 8-bit data. Okay? Each address identifies an 8-bit data. Okay? So if the address difference is 1, so which means that the data size, the data space between these addresses is 1 byte. Okay? And then RISC-V memory. RISC-V memory employs the little endian memory type. So I will explain later. And then does not require word to be aligned in memory. So which means, so word is 4 byte. Okay, so usually it means if we just use the load word is the load word instruction. So it means that it transfers word data. So which means 4 byte of data. But when the load word accesses memory, then the address does not need to be multiple of 4. So this line explains this. Okay. So which means the address of load word can be 3 or 6 or 7, also 8. Okay. Not multiple of 4. Okay. Okay. So it's not critical actually. So, but you need to understand the little endian. Okay, let's learn about the endianness. So actually there are two types of data allocation approach. So little endian and big endian. So it is because even though we use the byte address, but usually the CPU handles the larger data. So for example, we frequently use the 4-byte data. Uh, so for example, in C, if you declare integer type data, right? Then what is the size of integer? We can check the size of integer using the size of function, right? What is the size of integer? It's a 4-byte. So what is the size of float? 4-byte. Right? What is the size of double? So I believe most students took the C, right? What is the size of a double? 8-byte, right? Huh? So anyway, we handle larger data usually, even though we use a byte address, so we handle larger data. So which means also the size of the 32-bit, the size of registers in 32-bit computer is 32-bit is 4-byte, okay? Which is 4-byte. So usually we handle the larger data. Then how can we allocate this larger data in memory? So there are two types of approach, the little endian and big endian. So let's see the example. So this is the 32-bit integer, okay? So it's the 4-byte. And then we want to store this 32-bit integer to memory. Then, hexadecimal number, 2 digits represent 1 byte, right? So let us assume that we store this 4-byte data to the memory. So this is the memory address A. So like we store this data to address A. Then how can we store this data? So little endian means that LSB of data has the smaller address. So what does that mean? So this is the LSB. So this is the pin number 31 down to 0. Okay. So this is the least significant byte. Okay. So LSB, usually LSB represents the bit LSB, the least significant bit. But you know, this is the smallest address, so like A. So when the this 32-bit integer is allocated in the memory, then LSB is allocated to the smallest address, like A. Then this one, the next byte becomes the A plus 1. The next byte becomes the A plus 2, A plus 3. So these 4 bytes of data is stored like this in the memory. Okay. So in the memory address A, 0D is stored, and then 0C, 0B, 0A. This is the little endian type. And then RISC-V uses little endian addressing type. And then the opposite approach is big endian. So big endian is different. The MSB is assigned to the smallest address, like A, and A plus 1, A plus 2, A plus 3. So it is allocated to the memory like this. So if you see this uh, different types of endianness, then you can find that even though the instruction is the same, but the memory can be the data can be allocated to the memory in a different approach. Okay. So, but usually RISC-V uses little endian type addressing. Okay. Okay, then let's see the byte address. So, okay, so each byte data has its unique address, and but as I mentioned, we frequently use word type data because the integer, so we frequently use integer or float type data. There is a floating point data. So these data just occupies 4 bytes of data. So we frequently use word type data. Okay. So sometimes we can use the word address or byte address. So if we just use the terminology address, okay, address, then it represents the byte address. But in some questions, so I may use the word address. Then it means the word address means that it means the address of word data. So which means it's the 4 byte of data. So you need to distinguish this one. So let's see the example. So this is the byte address, and then each address uh, each address maps to the 1 byte of data, like 0, 1, 2, 3, and then 4, 5, 6, 7, like this. And then you can think that this 4 byte, this 4 byte data is the word data. Okay. Then the address of word can be the multiple of 4 like this 04 8C 10. But so actually when in the question, so when we mention the word address, then it can be represented like the 0, 1, 2, 3, and 4 like this. Okay. So it means the address of word. Okay. Okay. And the data. So as I mentioned, the 2 digit of hexadecimal number occupies the 1 byte of data. So data can be stored like this. Okay. So, the memory is a data array. So you can just understand how the data is allocated in the memory using the address. Okay. So let's see the example. Let's see the example of load instruction. So this is the example of load instruction, but you can find that this is the load word. Okay, so I explained about the 2 different types of memory instructions, like load instruction and store instruction, right? But there are different kinds of load and store instructions based on the size of data to be transferred. Right. So the same load instruction can transfer byte data or half word data or word data or double word data. Right. We can just define different type of load instruction. When we transfer data, then we need to identify the location of data, right? The location in the memory, and then location of register file, and size of data, right? So based on the size of data, we can define different type of load instruction. So like the load byte is the LB, load half word is the LH, and then load word is the LW, and then load double word is the LD. So it is a 1 byte, 2 byte, 4 byte, 8 byte. Okay. So in this example, we use the load word. So what does that mean? This load instruction transfers 4 bytes of data from memory to register file. Okay, so this is the load word. So which means this is the load 4 byte, and then S3. What is S3? This is the register name, ABI name, right? So this is the destination. Destination is the register, and then this one represents the address. Address in memory. Then what address? This is the byte address, right? So if we just use the address, which means it's a byte address, okay? So this is the byte address. So what does that mean? So how can you calculate this address? So you can find that this is the 0 and 8. So which means it's the 0 plus 8. So this is the offset, which means 8. So the 0 register. So actually the load reads data from the register, okay, and then it uses the this data as the base address, and then add the offset. Offset is the 8 in this example, okay. So in this example, the 0 always has 0 value, right? So it's a 0 plus 8. So target address is 8. So we know the location in the memory. So this is address 8. And then the destination, the location in register file is S3, and size of data 4 byte load word. Then how can we access the data? So, oh, this is the 8. So find the address 8, right? So it will access the address 8. And then what is the size of data? 4 byte. So it will access these 4 byte. So it will this load instruction will read data in 8, 9, A, P. Okay, so 4 byte. So this is the address, the first address of the 4 byte of data. Then, so if we just check the data, then this is the data. Okay, 01 FE EE2842. So this data is read from the memory, and then this data is stored to S3 register. It's a register. So this is the 32-bit data. So 32-bit data is just stored in the register S3. So do you understand? So this is the load instruction. Okay, and then load instruction works like this. Store. So store instruction, the direction is just the opposite. Okay, so it reads data from registers, and the read data is transferred to the memory. So store instruction also requires the location in register file, the source location, source register, and then the location in memory and data size. Okay, so in this example, we use the SW. So you know W, each word, like the load instruction, is 4 byte. And then store instruction also start with the register name, the register number or ABI name of the register. And but this register is the source register. Okay. So store instruction reads data from the source register, and then this data is transferred to the memory. And then like the load instruction, this is this part calculate the address in memory. Then how can you calculate? With the same way, this is the offset, this is the base address in the register file. Okay, so how can you calculate? It's the 0 plus 0x10 0. So it's a hexadecimal number. So which means it's the 0 plus 0x10 0. So 0x10 10. This is the address. The address of target address of store instruction. So what does that mean? The direction is different. So it's a T7. So it just read data from the register file. Okay. The register is not here. So it reads data from the register file. So like T7. Okay. And then let us assume that T7 has the AA, BB, as you can see, CC, DD. Okay. T7 has the AA, BB, CC, DD. Okay, it's a 32-bit data. Okay, so this data read from the register file, and then what is the target address? Target address is a 10. Okay, 10 is here, but the size of data is 4 byte. So in the same way, store instruction will access this amount of memory space from the address, and then 4 byte. Do you understand? So in the load instruction, address and then size of data is 4 bytes, so it will access this amount of data. And then store is the same, address 10, and then size 4 byte, access this amount of data. So it reads AA, BB, CC, DD from the register file, and then it will store this data to this space in the memory. And RISC-V uses little endian address type. So AA will be stored in the address 13, right? BB 12, CC 11, and then DD 10. Okay. So this is the store instruction. Okay. So try to understand this. Okay. But it's just the rule. Okay. It's just the definition. So try to understand how the data is allocated in the memory. So, okay. And then also you can just understand the direction of data transfers, and then the size of data, right? So this is the example. It's a C code. The C code, the read the H, data H, and then plus A, and then 8, and then it is stored to the array A index with the 12. And then you can find some condition here. H is in X21. Okay, so which means the data H is in the register file, but A8 and then A12 is in the memory. But then what is the base address? Base address of A. What is the base address? So, if you declare an array, then it will start with the A0, and then A1, A2, A3, blah, 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 blah. Okay, let us assume that this type is integer, 4 byte, right? Then base address of array A is the address of A0. The address of the first element in an array. So this is the base address. Then what is the address of the next element? So the size of A0 is 4 byte. So address of A1 is the address of A0 plus 4. Right. And next is the A0. Okay, oops. A0 plus 8. Okay. So this is how the array data is stored, allocated in memory. So base address, the base address is the address of the first element. Then we can just increment the address by the size of a single element. Okay, do you understand? Then what is the address of A8? It's the base address A plus, so element number is 8. Then what is the offset? Offset is 8 multiplied by 4. It's a 32. Okay. So we can calculate the address of an array element like this. Okay. So let's see the example. Uh, let's see the RISC-V assembly code. Okay. So you can find the load word. The load word x22 and then offset is 32. So what does that mean? So in this example, I assume that the base address of A is in the x22, right? So what does that mean? This one. So I mentioned that in the load instruction, this part calculate the address of data, right? What is the address? Address is x22 plus 32. That's what I explained. Okay. So read data from this address, and then data is stored in x9, right? So it means this one. It is the A8. And then we need to perform addition. So H plus this one. So H is here. And then the data of A8 is stored in X9. So it's the X9. And then it's stored in the also X9. So, 812. 812 is in main memory, right? So the data, the result needs to be stored in main memory. How can you calculate the 812? With the same way, the base address of A plus is 12, offset is 12, the index is 12, and then 4, H48. So this is the address of store instruction, and then store instruction with the data from the register, then it is stored in the main memory. Do you understand? Okay. So, and then some of students can notify that I use the AND operator here. Okay. So actually it represents the address of data, right? So so I believe so I know that in this course there are uh, some students from other department, right? So but actually in the CS department the C language, I believe the C language is the mandatory course. So actually in C we can use the pointer type data, right? So it's kind of very some tricky part in C, right? But actually the pointer represents the address of data, right? So, and then so that's why I use the AND operator. So this operator. So so if we use this operator, then we can store the pointer data in the pointer type variable, right? But actually, the pointer is it's similar to the address of data. So that's why I use AND operator to represent the address of data. Okay. Okay. So you need to understand actually. So that's why the C is it's uh, tightly related to is coupled with the hardware. Okay, so it's kind of some low level language compared to the other languages. It is because in C we can access the actually memory with the pointer. Okay. Okay, so let's see. Okay, so then so I just explained this because you need to be familiar with some my notation, like this operator, and operator, and pointer in C. Okay, so so in A is declared. In C, a variable is declared. So you need to understand that if a variable is declared, this space, the variable is allocated in memory. Okay, you can understand like this. Variable is declared, variable is allocated in the memory. So the data of this data variable is in memory. So using the printf function, if we just write the code like this, then we can just see the value of A, value in A. But if we write the printf code like this using the AND operator, then this will return the address of A. Okay, that's why I frequently use the AND operator to represent the address. Okay, so you can understand this operator like this. Okay, so then you can see this value. This value is the address of A. Okay, you can just apply this same code to the array data. Okay, you can just check the address of array element. Okay, so pointer. So pointer is, so as I mentioned, the pointer is the a kind of tricky part in C. But so you can just understand the pointer like this. It's address of data. It's a little bit different, but you can just understand like this. Okay, so register versus memory. As I mentioned, register is faster, much faster. The memory is so slow because the size is so large. Okay, so actually in a RISC-V, the data processing, the arithmetic instruction and most instructions just access register data. Okay, only memory instructions such as load or store instructions access memory. Okay, so which means in order to process the data in the memory, the data needs to be transferred to the register using load instructions. Okay, then arithmetic and logic instructions. So no more instructions just to handle data in registers. Okay, so actually the registers are very precious resource. So the compiler needs to manage registers because there are the several numbers of registers in a CPU. Okay, the size is so small. Okay, so this is the kind of load instruction, kind of load and store instructions. So as I mentioned, so if so there are several kinds of load instruction and then several kinds of store instruction. Okay, like LB, LH, LW, and then if we use the 64-bit RISC-V instruction, then we can use the LD. Well, if we use the 128, we can use the LQ. Okay, but you can find the LBU and LHU. So it is because so sometimes we need to handle the unsigned or signed numbers. Okay, so that's why the load instruction has the LBU or LHU. So I will explain later. The store instruction has also SB, SH, SW, SD, or SQ. Okay. Okay, so we learned about the memory instructions, and then I will briefly explain about the signed and unsigned numbers. Uh, so actually we are learning about the integer instructions. So integer means that it's a 정수 in Korean, okay? But so we can just use the signed number or unsigned number. And then what is the signed number? The signed number, the every bit represents the positive number. No, no, no. So unsigned. So did I say unsigned? So unsigned number, every bit represents the positive number. Okay, and that's the size of the number. But so this is the unsigned binary integer. So every bit just represents the the positive number, and then size, and then every digit represents the size. Okay. So range is the 0 to 2 to the power of n minus 1. Okay. Then this is the range. But in the 2's complement signed integer. So in the computer system, so we use the 2's complement number, right? So that's what actually that's what we learned in the uh, digital logic design course, right? In the signed number, the MSB represents the negative number. Okay. So if we just check that if the MSB is 1, then it means the negative number. And then size of negative number is like this. This amount of negative number. Okay. So the range is like this. So you can find the range like this. So if we use the signed number system, then if the MSB is 1, then it means the negative. If the MSB is 0, then it is the positive. Okay. But in the unsigned number, if MSB is 1 or 0, then all cases are positive number. Right. It's unsigned and signed. Okay. Using the unsigned number, we can just represent only positive numbers. Okay. So this is two's complement number system. Okay. Using the sign bit is the MSB, then we can know the sign of this number. Okay. So then how can we change the sign of this two's complement number? That's what we learned. Okay. So by negating all bits and then plus 1 becomes the minus x. Okay. So that's how we just change the sign of signed number, two's complement number system. Okay. That's okay. So this is the example. It's a plus 2 is a 0, 0, 1, 0. And then in order to make minus 2, then we need to invert all bits. So 1, 1, 1, 1, 1, 1, 0, 1, and then plus 1. Then this becomes the 1, 1, 1, 1, and 1, 1, 1, 0. Okay. Okay. So, and then this part is important. Sign extension. Okay. So actually, that's what we learned. So, and then this is just definition. Okay, so you need to memorize. So this is just the definition, right? Okay, but the sign extension. So sometimes we need to handle the different size of data. Okay, so for example, we may read the 8-bit data, and then we can make the 16-bit data. Okay, then sign extension means that when in order to make the larger size of data, okay, then we need to extend the number of bits. Obviously, this is the 8-bit, and then this has data as the 16-bit. So sign extension means that when the bits are extended, then we need to repeat the MSB. If the data is the signed number. For example, if the +2, we need to just repeat the MSB 0000. -2, then you need to just repeat the MSB. Okay? How about the unsigned number? For the unsigned number, we can just repeat the 0. Okay? So that's why LB has the signed extended load or LBU, the zero extended load. So we need to use the LB for the signed number and then LBU for the unsigned number. Okay. Why? What is the LB? It reads byte data, 8-bit data from memory, and then it stores this data to the 32-bit register. So what is required? Bit extension is required. Okay, so 8-bit data needs to be stored in the 32-bit data space. Okay, so if this data is the unsigned data, then we need to use the LBU. So which means we need to apply zero extension. Okay, so remaining bits, we need to just use the 0 for LBU. But if we use the LB, then it assumes that the target data is signed data. So which means it just repeats the MSB, the signed bit. Okay, and when this data is stored in the register. Okay, that's why LB has LB or LBU. So you can just understand that the default data value is the signed data. If we just don't handle the unsigned data, then we can use the LBU. Okay. Okay. So I will stop here. Any question? Okay. Thank you. Thank you for your attention. See you in the next class. 감사합니다.